Okay, maybe we can get started. So welcome everyone. We're delighted to have you here for the next Vinberg Distinguished Lecture. Today, our featured speaker is Professor David Kazhdan. He earned his doctorate under Kirillov and was a member of Gilfan's school in the Soviet Union. He moved to the US in 1975 to take a professorship at Harvard. And then in 2002, he immigrated to Israel, to the Hebrew University of Jerusalem, where he is now. He's a recipient of many awards and prizes. He has a MacArthur Fellowship. He's a member of the US National Academy of Sciences, the Israel Academy of Sciences, the American Academy of Arts and Sciences, many other awards, including the Israel Prize in 2002, and just a year or two ago, the $1 Million Shaw Prize. I could go on and on, but it's a great honor and pleasure to hear from him. So thank you for joining us, and Professor Kazhdan, please take it away.
Yeah, I remember Vinberg very well, and very fine memories, and thankful for the possibility to participate in this lecture series. The goal of this talk is to present results and conjectures of joint work with number of people, we see their names, on the extension of the Langlands correspondence. To start with, I remind a special case of the classical formulation of this correspondence. While this correspondence is not yet established in full generality, it has powerful applications such as the proof of Fermat and Sato-Tate conjecture. Also, the categorical version of correspondence led to a number of important results in algebraic geometry. So let us start. Let E be a global field. It means either number field or field of rational function over a curve or a finite field. And A, the corresponding ring of Adel. Langlands conjecture the existence of correspondence between automorphic representation of the group of matrices over Adels and n-dimensional representation of the Galois group of a field. More generally, the conjecture outlines the correspondence between automorphic representations of the group G and homomorphism from the Galois group to the complex dual for an arbitrary split reductive group. I restrict my presentation to the simplest possible case when the group is PGL2 and therefore the dual group is SL2. And I'll only consider the unramified part of the correspondence. To formulate this correspondence, we have to introduce the notion of a spherical Hecke algebra. So let F be a local non-Archimedean field. O is the ring of integers. T is a generator of a maximal ideal. And K is the residue, finite residue field. I denote by HF the Hecke algebra of complex valued compactly supported two-sided G of O invariant function on JF when the product is defined by convolution. And by TF, a characteristic function of this double cassette. It actually generates, in this case, the full Hecke algebra. So instead of considering full Hecke algebra, I mostly talk about this particular action about this particular element. Now, it is easy to see that if you have any smooth representation of the group G of F on a vector space, it induces an action of a Hecke algebra on the subspace of G of O invariant vectors. So just apply. Now I'll formulate unramified Hecke correspondence in this case. Let E be a global field. V, or this script V, the set of finite places, A the corresponding ring of adels. For any V we define by E the completion of E, and by O V the ring of integers, and consider corresponding Hecke algebra and the special element in it. Let K be the standard maximum compact subgroup, and X the set of double cosets. Algebras HVX natural on this space, as I explained before, and generate a commutative algebra of self-adjoint operators on the Hilbert space. We define a map from function on X to functions on X cross V by applying Hecke operator in every point. Now this is conjecture of Langlands. It says, so let now GE be the fundamental, which I didn't, GE be the unramified for any, before a Galois group. And the conjecture says that for any bounded unramified homomorphism, there exists non-zero function, which is eigenvalue of the corresponding Hecke operators, where eigenvalues are determined as a trace of value of this representation on Frobenius. I will consider geometric case, so let me special case, geometric case. So in this case, we can our field is field of functions on a curve of a finite field. We can identify the set of places, with set of geometric points of our curve, and we can identify, as was discovered by Andre Weil long ago, the set of double cosets with the points, k points of groupoid, of a stack of principal G bundles on our curve. This is a discrete groupoid, as every groupoid has canonical measure. Such a measure of every point is inverse of the order of the group of automorphism of the corresponding object. In this case, we have a geometric interpretation of a Hecke operator, which will be central for all our discussions. It's based on the following very general construction. So suppose you have a stack Y. We denote by S of Y, K stack, where K is a finite field now. We define S of Y space of complex valued function with finite support on this set. And if you have a morphism between stacks, we have the corresponding pull back and push forward on the space of functions, which defined is a natural way. Pull back is just pre-composition, and push forward is summation along the fibers, and since fibers are finite, there is no problem in the summation. In this way, we can find geometry. We consider very special case. We consider Z, which is Hecke correspondence. This is a stack of quadruples where F and G are bundles, PGL2 bundles on the curve. V is a point in the curve, and I is the embedding of one bundle into another, such that the portion is one-dimensional and supported in the point. We have natural projection maps from these correspondence to 1P is a projection to the bundle, to the stack of bundles, and Z and Q is a projection on the product, which can be defined in a very natural way. Now, the claim is that in this language allows geometric interpretation of a Hecke operator, which was defined earlier. And it is just composition of pull back and push further along these two maps. For any point, K point on the curve, we denote operator TC, which is a restriction operator T on this fiber. Then this operator TC, if the commuting self-adjoint endomorphism on the Hilbert space, generate and commutative algebra. In this case, let's continue, we'll come back. In this case, we can define the notion of Cuspidal form, a constant term, and the Cuspidal functions. So let's pick the group of line bundles on a curve defined over K. For any pair of PGL2 bundle on a curve and a line bundle, we denote by I of L and F the number of lines of bundles. We take some lifting F tilde of F to PGL bundle, so it comes from some GL2 bundle. We choose some representing GL2 bundle to consider the space of line subbundles with this normalization. It's easy to see that this number doesn't depend on the choice of representative. Using this function I of LF, we define a linear map from functions on G bundles to the function on line bundles, which is defined the kind of the easy formula. You can write it also in geometric terms, but I will not do it. It doesn't help me. And we denote by define Cuspidal function and subspace of function on bundles with zero constant term. Now it is easy to see that this subspace is finite dimensional in H invariant. The Langlands correspondence, proved in this case by Drinfeld, implies that space of function, Cuspidal function, is direct sum of one-dimensional H invariant subspaces parameterized by irreducible homomorphism from the fundamental group of a curve to SL2. Now, so this was kind of a reminder of what is a very special case of Langlands correspondence proved 40 years ago by Drinfeld. Our work, which I present, is an attempt to extend the Langlands correspondence from the field of rational function of recursive a finite field to the case of fields of rational function on a curve defined over a local field. To simplify notations, I will assume that the genus G of my curve is bigger than 1. One can formulate appropriate statements for genus 0 and 1. In some of our work is done really in case of curves of genus 0, but it's easier to formulate the all definitions in the case of curves of genus bigger than 1. Now I'll formulate a number of conjectures. Some of these conjectures actually follow from one conjecture in algebraic geometry, which we proved for the curves of genus 2 and generic curves of genus 3. When I talk about present conjectures, I put star at conjectures which could be derived from this conjecture in algebraic geometry. So I start my talk with kind of presentation of conjecture in algebraic geometry. It's kind of easy to formulate, but seems not to be so easy to prove. Okay, so we fix a curve with purely algebraic geometric conjecture. We consider the scheme of stable vector bundle of the curves of genus G. We consider a scheme of stable vector bundles of degree 2G minus 1. And denote by peak 0 the variety of line bundles on C of degree 0. For any stable vector bundle, we define a scheme of pairs of line bundle of degree 0 and a section of the tensor product. The conjecture is that for any stable bundle E, the scheme is reducible of dimension G and with only rational singularities. So it is purely algebraic geometric conjecture, which kind of we can prove for genus 2 and 3. Now, we want to define Hecke operators. The kind of a problem in definition or Hecke operators is that before, in the case of curved or finite field, we consider it was Hecke correspondence when the new Hecke operators came from Hecke correspondence. And the Hecke correspondence acts as a composition of two operators, the pull back and push forward. Push forward was summation along the fibers. And over finite field, the fibers were finite. In the case of local field, it's finite dimensional variety. So if F is QP, it's finite dimensional periodic varieties. And summation of fiber requires a careful definition. But to start with and to formulate the definitions, we start with some kind of very general notion. We say notion of smooth functions on F point of algebraic variety, F variety, where F is a local field. Local field could be Archimedean or non-Archimedean. So the definition is the following. The set of F points of X is a bounded natural topology. And if F is non-Archimedean, we say a function is smooth if it's locally constant. If it's Archimedean, we say the function is smooth is locally there exists embedding in a smooth variety and a smooth function of this variety whose restricts to our function F. We can define the C infinity of X, the space of smooth function, as S of X, the subspace of function with compact support. This definition can be extended to section of line bundle. For any line bundle over X and any complex number chi, we can consider complex line bundle on the set of F points, which is due by L from the homomorphism where norm cut, which shows the power of norm, where norm is a canonical norm on local field. Since line bundles are locally trivial in respect of natural topology, we can apply the previous definition of smoothness and define spaces of smooth sections and subspace of compactly supported smooth sections. The case which we're mostly interested is the case when X is smooth. In this case, the smooth sections of normal canonical bundle are the same as smooth compactly supported. And what's even more important for us, sections of square root of normal canonical bundle are compactly supported half measures, and there exists natural Hermitian product because the product of two half measures is a measure, and you canonically integrate. So we denote by L2 of X the Hilbert space completion of this space. Now, the band is a stack, and when it's not easy to develop, not immediate to define the notion of function of the stack. So we actually, my talk will contain three different spaces one can associate, which can interpret the function of the stack. The first definition observe that there exists open dense subset of very stable bundles on a stack, and we define our space as a space of half measures on this open subspace. Since if you in general consider open dense set in some space, the L2 of this open dense space is the same as L2 of the whole space. So the replacement of band by open dense subsets is not important while we're talking about Hilbert space. Now a definition. A bundle is very stable if there is no non-trivial morphism from F to its twist by canonical bundle, which is important. In this case, square root 0. Doesn't matter, I will not. Well, what's important is this substack is actually a smooth scheme. And therefore, we can define the Hilbert space of half measures on this smooth subspace. We fix one for all the square root of canonical bundle, and and denote, it defines the square root of canonical bundle on band. Now we can try to define Hecke operators. So as before, we have a Hecke correspondence. It's purely algebraic thing. For any point, F point on a curve, we define the fiber of the project of Q on this point. Now there is the following result, that if you take pullback of square root of canonical bundle and restrict it on a fiber DC, then this sheaf is isomorphic to canonical bundle on a fiber twisted by line, which is kind of line of minus square, essentially, or inverse of square root of canonical bundle on the curve. It's a corollary. It means that if we take, there's something I skip, which is not good. Sorry, I missed one line. That's all right. So I denote by V, which I somehow forgot to bring here, a space of smooth half measures of band, and on VZ by V0 subspace of V which are compactly supported. So what you see now, that if you take any half measure on band, pull it back on Hecke correspondence, and restrict it on a fiber, you obtain a smooth measure canoe on a fiber with values in a line. So you can try to define now the Hecke operator by, since pullback of F is a measure essentially on every fiber, you can define Hecke operator as the integral of pullback along this fiber. The problem is that fiber is not necessarily compact, and therefore we cannot guarantee that integral is convergent. So our first conjecture is compactness conjecture. It says that for any V0, with smooth compactly supported half measure on band, the integrals are absolutely convergent. So if so, we can consider TC as a map from V0 to V twisted by some line. The second part of conjecture is that TC actually extend to family of commuting self-adjoint operators. These two, I put stars here because these two statements essentially could be deduced from the algebraic geometric conjecture. In particular, they're known for genus 2 and generic curves of genus 3. The third conjecture is that those operators not only bounded self-adjoint operator, they're compact and they don't have a common kernel. Now I assume the validity of the compactness conjecture. If so, we can consider operator T, which is all TC together, as a section of a line bundle on curve, F points of curve with value and endomorphism of H. So, given any section theta, we can describe the corresponding eigenvalue, eigenspace. We can consider theta as an eigenvalue and consider eigenspace. It means we consider elements in the Hilbert space such that which is eigen functions or eigenvectors of the Hecke operator with eigenvalue defined by theta. And we describe this defined spectrum as a set of sections, that means eigenvalues, which really appear in our Hilbert space. Now, the Langlands correspondence is a conjectural description of this set. In the case of finite fields, which really have kind of this Langlands conjecture, the Rydberg theorem, gives us description in terms of representation of fundamental group of a curve in SL2C. So we hope to have similar type of description of the spectrum for local fields. As it is now, we have such description only Archimedean case, when in addition to Hecke operators, we have another player, the algebra of differential operator, twisted differential operator on band. The spectrum is over. For lack of time, I'll consider the only Archimedean case. I consider the case of F equals complex numbers. The case of real numbers is possible, just I don't have time to discuss. So we start I start with definition of an opera. SL2 opera on the curve is SL2 bundle with holomorphic connection and a subbundle, one-dimensional subbundle. Such a connection connection defines natural morphism. Yeah, and we require that the morphism is isomorphism. Opera C is a variety of operas. For any opera, we can denote by G hat the corresponding smooth bundle on complex points of our curve. Our curve is defined on C. And holomorphic connection inducing a flat connection. It's essentially Riemann-Hilbert correspondence. And we denote by zeta O, where O is opera, the representation from fundamental group of our curve to SL to C, defined by connection. Of course, this representation defined up to conjugacy. We define real operas. And the substantive operas such as homomorphism could be realized inside of SL2R. Now, so omega to 1/2 is a line bundle on band, and we consider the algebra global sections of regular differential operator. The following result is proved by Bellinson and Drinton. The algebra is commutative. Its spectrum is the variety of orders. Now, we want to say, okay, we have algebra, these differential operators naturally act on the space of smooth functions, so smooth half forms on a band, and also conjugate differential operator, complex conjugate also act on this space of smooth half forms. So the tensor product, A with the tensor product with algebra X, we define involutions, very simple involution tau, and denote by AR the subalgebra of tau fixed elements. We want to say that algebra AR commutes with Hecke operators. But since the algebra consists of unbounded operators, we have to specify a subspace on which both A and H act. So we define the Schwarz space. The Schwarz space, as usual, is a space of all functions, all half forms, such there's no V0 here. This is a mistake. We consider all half forms on band such that after application of any of our differential operators, it still are in L2. So now we can formulate conjecture. First of all, that for any operator in a real part of algebra, the operator A bar, which defines on the dense subset of L2, has canonical self-adjoint extension to band. The space, Schwarz space, is stable under the action of Hecke operator. The action of A commute with Hecke operator. Now it makes sense because they both act on the same space. And essentially, the whole space is direct. There exists a dense subset in Schwarz space spent by eigenvalues on the one-dimensional subspace, which eigenvalues of both A and H. So the Schwarz space conjecture implies, let us say, this direct direct sum of eigenspaces by eigenvalues. It follows from this result of Bellinson and Drinfeld, we know the spectrum of A is square of space of orders. Since elements in R are self-adjoint, we see that second component is completely determined, and therefore now we want to consider for any operator, we consider subspace in H, which is a subspace of algebra corresponding to this eigenvalue. We can show that this space is always cannot have dimension bigger than 1, so it's either 0 or in dimension, and it is 0 if it is operator is not real. Conjecture is that converse is true. In a sense, we have description of spectrum of algebra A, and in the second will be algebra Hecke operators in terms of real operators corresponding to dual group SL2. So this is kind of very natural variant of Langlands conjecture with spectrum of Hecke operators. In the second they appear, Hecke operators on band, on function on band, is described in terms of representation of fundamental group into SL2. In this case, it's not a representation of fundamental group, but operators, which is kind of thing very close to representation. You can say representations which come from opera. Now we have one more thing which you can define here. So suppose we have some opera such that the corresponding eigenspace is non-zero. Since Hecke algebra commutes with algebra A, this implies the existence of a section of this bundle such that restriction of Hecke operators on the subspace HO is given by value the section at a point C. Right. Now we have a conjectural description of this section. In other words, what we see that any operator should, any real operator, should define some section of this line bundle on the curve, on the complex curve. And here is conjecture, which I could even, which follows from algebraic geometric conjecture. So let's kind of describe a very particular section. We consider an embedding just by the it should be -1/2. Anyhow, opera defines a particular section of this our sheaf twisted by omega to 1/2. Since opera is a real opera, then there exists an isomorphism between smooth bundle in the complex conjugated. And therefore, we define, so sigma is section of the bundle, sigma bar is a section of the complex conjugate. And conjecture tells you that this section FO is just a norm on this section.
Okay, so welcome back to the second half. Please take it away.
Now, in the contraction of a Hilbert space, we replace groupoid by its open dense subset. As I said, such replacements is inconsequent because the definition of Hilbert space for a definition of Hilbert space, but it's not good to defining a Schwarz space, which is important for us. So I outline two different constructions of Hecke operators acting on a different. Now, okay, right now I outline the construction of an action of Hecke operators on another vector space and provide conjectural definition of a map from this space to H, commuting with the action of Hecke operators. To define this space as prime, we have to extend the definition of smooth sections from bundles or line bundles from schemes to stacks, since we really want to define what is the corresponding space of smooth functions, of smooth half forms on the stack of bundles. We have to give a different general definition. So we say that algebraic stack is admissible if it can be presented as a quotient of a smooth variety by the action of GLN. Such realization is admissibly presented. One can show that the stack is admissible. Stack is union of admissible substacks. Okay, I didn't yet define the spaces of smooth function on admissible stack, but what's important that it's covariant under open embeddings, and these embeddings become isomorphism for big R. So we will consider bond as an admissible stack. Okay, so let y be admissible stack of finite type, and we have a admissible presentation, and we have a line bundle, which I didn't say, but we have a line bundle. Now we define space of smooth sections of line bundle on a stack in the following way. We consider line bundle function section with compact support. On X is a smooth scheme, so we know what does it mean to consider section of pullback of a line bundle. And the group GLN X natural in this space, and we take a space of coinvariance. So if F is not Archimedean, it is just coinvariance. If Archimedean, we have to take it in the corresponding category of Frechet spaces. So this is the definition of smooth functions or smooth sections of a line bundle on a stack. Now, let's assume, which will be next time, that our admissible stack contains an open substack, which is smooth scheme. As remember, this will be true for bond. We denote by U, Y, divided by U, the preimage of this substack, and by P the corresponding quotient map. Okay, let N be canonical bundle on our stack, and YX Y the relative canonical bundle. So now, if S is compactly supported smooth, let S be compactly supported smooth section of a complex line bundle. Then the restriction U is, of course, section of restriction of corresponding line bundle. In particular, along the fibers of projection P, it is a measure. And therefore, we can try to define the push forward as the integral along fibers of P. And if we succeed, we get a section of a corresponding line bundle on our smooth scheme. But the convergence of these integrals is not guaranteed, since the intersection of support with fibers is not necessarily compact. So we just give a definition. We say that the pair is nice or kappa nice if the corresponding push forward is absolute conversion defined as smooth section. And we say the pair is excellent, even nice for all kappa bigger or equal than 1/2, and for 1/2 push forward lies in L2. Then it is half measure on it's half measure on the smooth variety, and there if it lies in L2, we have a natural push forward. So if Y is K nice, the map defines the map. It's excellent. We have a projection into Hilbert space. So example, which is kind of special example of our case, but it's easier to see what happens. Let's consider the case when G acts on P1 naturally, and X is the cube of P1. X, of course, acts diagonally on G, and we denote that U the complement to all diagonals. That means to consider some triple of points in P1, which are all distinct. Now the group acts freely on U and transitively, and therefore the corresponding quotient space is just 1 point. So we can check that in this case, the stack is nice for all K bigger than 1/3, in particular for 1/2. And since the corresponding space consists of 1 point, it's definitely excellent. Now we can define, now we consider special case when our Y is bound. And we consider our space is space, so it's a half form on band. In this, it's very easy to see that our Hecke correspondence defines operators acting in this space. Now it's essentially the same as before, but now fibers are compact. And therefore Hecke operators are well defined, and they define commuting operators on this space. But this space does not have itself any natural Hilbert space structure. So conjecture is that the stack band is excellent. So we have a map from this space as prior to space, Hilbert space of half measures on very stable bundles. This map commutes with action of Hecke operators. It's almost automatic if it's defined. If F is Archimedean, it also commutes with action of algebra A. And this is important conjecture, which we don't know how to prove, that map is actually embedding and its image in the Schwarz space. So it's natural state. Schwarz space should be defined. The natural space is space of half measures on band. And essentially, we say that our Schwarz space is really a space of half measures, small half measures on band. Now we consider a case of a non-Archimedean field. In this case, once more, we have a generator of a ring of integers in our local field. We have quotients of which kind of case periodic field with Z mod P to the NZ. We can consider a space of complex valued function finally supported on this space of all pointed band. And we have pullback in uses defines a map. Now I have to say it defines a map. So it's now I will assume we can ask how is it possible that we start with functions and come to section of half forms. The thing is that since our curve is defined over, we assume that C is defined over ring of integers, then it's all canonical bundles are all defined over ring of integers. In their norms are complete, which we use normal canonical bundle are canonically trivialized. And therefore, we can identify functions with sections of any power of canonical bundle. So this mapper n really defines linear operator. Now, this linear operator is not an embedding. One can show, one can easily see the dimension, even for n equal 1 dimension. In the n equal 1, our space V, space of functions on G bundles defined over finite field, and the space is infinite, and therefore corresponding set of bundles defined over finite field is infinite, and therefore dimension of the space infinite. On the other hand, one can prove the dimension of the image is finite. So this is not an embedding. Now we'll consider a third approach, which gives you more information of what is going on. But this approach makes sense only for non-Archimedean field. Until now, we consider any local field. But the third approach works only in the case of non-Archimedean field. But in some sense, this is most interesting for us, because for Archimedean field, we really have a conjecture, Langlands conjecture of defining a spectrum in terms of a dual group. It will be very, will be very interesting to do it for non-Archimedean field. So I start with some construction, but stop in the middle. Okay, so Hecke correspondence, as usual, gives us such morphisms. In particular, we can restrict this morphism to ON point. You remember ON is a finite field with just quotient of O mod P to N. It's like Z mod P to NZ. This morphism define the morphism on ON points. And since fibers of Qn are finite, then defines linear operators. So we now can define Hecke operator exactly as before, modeling as before. We can define Hecke operator as a composition, pull back or push forward. In this case, like in the case of finite field, push forward is summation over finite set, and we define this operator, and they commute. In the case when n equal 1, we're back to the case of cursor finite field. So I will consider, to simplify notation, I will consider the next case when n equal 2. In other case, we'll consider bundles, points in bundle of Z, in case of periodic field, over Z mod P square. So as before, P is a group of line bundles on the reduction mod T square. Now we can define kind of a generalized Picard group, defined in the following way. Let D be a finite subset. Then we define big D as a set of coherent sheaves, which kind of almost line bundles. So the line between line bundles, TT line bundles, and the quotient is equal to supportive quotient is equal to D. We have a product, which kind of the product of corresponding bundles is essentially product of corresponding line and the product of corresponding line, but twisted by minus D. And we define for any bundle over 2 and L in P, we define a number as before, which depends on our bundle F, line bundle L, and subset D. It's number of subshifts such that A is big D, and the determinant is normalized as before. Now we also can define constant term and Cuspidal functions. For any D, we define constant term D, which is defined as the same way as before. We just sum over all bundles with weight, with weight defined by this function I, but now it depends on D. And we define cusp at the intersection of kernels of these bundles. Then stop. So the claim is that this space, as in the case of a finite field, is finite dimensional, that it's invariant under Hecke operators, and it has dimension more or less q to sig g. So before the dimension of corresponding Cuspidal function of a finite field were q to the 3g, and now is kind of q square over 3g, power 3g with q to the 6g. So we now can define the spectrum. Our Hecke operators act on finite dimensional space, and we can define the corresponding spectrum. Now we can ask what's the connection between this space and the space we started with. We have, assuming our compactness conjecture, we can define the map from this space to our space H. We first pull it back to S prime and then integrate over fibers. And you remember that I said the R2 prime is not an embedding at all, but the conjecture is that restriction to the Cuspidal function is a unitary embedding. We don't have much support or any support, I say, for this conjecture. I just would be glad if it were to. If it is unitary embedding, you see that this spectrum of the Cuspidal, Hecke operator Cuspidal part, is embedded in the spectrum of operators in the Hilbert space of half forms on stable bundles. And here I cannot formulate a precise statement, but I would expect that it's almost the whole spectrum. But I don't know how to say it precisely, so I skip it. And now the main question which we have is how to interpret we now obtain the action of Hecke algebra and find the dimensional space of Cuspidal. In the case when we consider Cuspidal functions over a field, the spectrum was parameterized by representation of fundamental group to SL to C. The question is whether this spectrum, which is much bigger, the spectrum of Hecke algebra on Cusp2, has any interesting interpretation. We don't have a guess, and it's kind of something which consider is the main question. Okay, I stop here and be glad to answer questions if there are any.
Thank you very much again for the beautiful lectures. Let's please unmute and we can all thank Professor Kazhdan. Thank you. So can I ask, has anyone done, a calculation in some cases to see if it's unitary, this last?
No, No, it's yes and no. There are some, first of all, this statement is already non-trivial on CUSP1. CUSP1 is a part of CUSP2, and you can ask the same question about CUSP1. In the case of CUSP1, there are some arguments why this should be true. But to make them rigorous, one has to prove some convergence. On some formal level, we have the arguments why this statement is true for CUSP1.
But for CUSP2, yeah.
For CUSP2, we right now trying to make CUSP, to get a rigorous proof in the case of CUSP1, and only then to go to CUSP2.
But at least these are finite dimensional vector spaces. So is it possible to?
Yeah, there is a finite dimensional space. You can ask about spectrum or Hecke operators. And this is well defined. For this, you don't need any conjectures.
Mm-hmm.
This definition exists. Conjecture is relation of this definition space with the other space I started with. But the space itself and action of Hecke operator are defined. So you can ask a question about spectrum, even though I'm asking a question about unitarity. It's finite dimensional space.
Very interesting. Other questions?
Excuse me, I'm trying to understand this. What kind of sheaves are those M, which are almost line bundles? Is it correct to say? I mean, it's.
I can give you an example.
Yeah, yeah.
Thank you. Just let's see. Let's consider the case when our curve is a fine line. So the ring is polynomials of x and t over t squared is 0. Take an ideal which generated by t and x. This would be example. And this is typical example. All these sheaves locally are on this form.
Okay. Okay.
You see, I can explain why they appear.
Yes, sir.
Like this. Suppose you have trivial two-dimensional bundle over this ring polynomials x and t mod t squared. And now take so it's a pair of function f and g, pair of polynomials. And now put an equation that xa plus tb equals 0. This will be some sub-sheaf in your, it will be, you consider set of such functions a and b which satisfy this condition. It's definitely O module. It's clearly this equation is variant. This O module will be of this type. So this kind of sheaves naturally appear. This kind of sheaves naturally appear in the picture. Well, but, yeah. So, okay, so this is why they appear. In a sense, it means you start with some line bundle, nice line bundle. You apply Hecke operator to your two-dimensional bundle, and your line bundle, you obtain some sub-bundle in the original bundle. Your Hecke operation is produced sub-bundle. Uh, so you appear a natural subbundle, but this subbundle is already not a line bundle, but slightly modified. So this is why, if you say, how do you prove that space of Cuspidal function is invariant of Hecke operators? Usually, you define kind of action of Hecke operators on functions on peak. You prove your constant term commutes with action of Hecke operators, and therefore kernel of constant term is invariant of Hecke operators. Here, to define the commutative diagram, you have to take into account not only usual constant term, but the slightly modified constant terms. Does this answer your question?
Well, I understand it slightly better. Thank you. Thank you.
Okay, yeah.
Thank you for the question. Are there any other questions? So if not, we can unmute and thank Professor Kazhdan yet again for the wonderful lectures. Thank you so very much.
Thank you very much. So
Thank you.
tomorrow I'll send you slightly modified.
Yes, yes, no problem. Yeah, if you
And then
send
it will not have your picture. Okay,
that'd be
thank you.
great. Thank you. And we'll see
Thank you
you
very
all
much.
next time.
Bye.
Bye.